Physics, more than any other science, has changed our lives in this century. Now, as the century concludes, the physicists are attempting things few of us can even imagine. Changing substance into energy, mapping the tiniest structures of matter, communicating with intelligent life in the universe, stretching and slowing even time itself, traveling among the planets in ships to be propelled by hydrogen bombs, and searching through the fathomless depths of space was something called the black hole, into which everything could disappear, never to be seen again. Plasma, the mysterious stuff of lightning balls and sparks. To man, frightening and dangerous, an alien thing. Yet plasma is the essence of the universe. The stars, the matter between stars, the clouds of dust and gas in the arms of the galaxies, all are plasma, matter in which every single atom is exploding.
So practically everything we see is in fact plasma. In fact, I suppose there are only two places where you have large concentrations of matter which are not in the form of plasma. One is on planets like the Earth, and the other is in neutron stars.
As we step outward past the moon into space, we will encounter conditions that only a few men alive today understand. They are the physicists, prophets of a different reality that we will have to know in the century to come. Andromeda, a light with 100 billion stars, a galaxy much like the one we live in. Most of the billion galaxies in the known universe rush away from us, but Andromeda does not. Physicists have discovered that Andromeda is joined to the Milky Way by gravity, somehow reaching across a gulf of space so vast that light takes 2 million years to cross it. Albert Einstein theorized that gravity is not a force at all, but a curving of space caused by the pressure of matter, just as a mattress curves when you sit on it. Until the 70s, physicists could do little to test Einstein's theory of gravitation. Now, with new tools, they are able to search the universe for the strange things he predicted. One of the strangest is the black hole. At the Institute for Advanced Study in Princeton, Professor Freeman Dyson.
The black hole is an object which has become so condensed that it has, so to speak, fallen through its own gravitational field and collapsed to a point where it can no longer be seen from the outside world. So it is literally a black hole, just a place in space where everything disappears, where nothing can be seen. All that you can tell from the outside is that there is a mass there because it has a very strong gravitational field. And it would be lovely to discover one of these things. As far as we know, we haven't yet seen one. But of course, it may be some of these mysterious objects that have been discovered are in fact black holes, which we don't yet recognize. It's quite clear that Einstein's theory predicts they ought to exist.
The very idea of the black hole defies the imagination. A place where there is nothing but gravity. The star which caused the gravity is crushed into nothingness, but the gravity remains, sucking in and obliterating anything that comes too close.
Once the matter has gone down the spout, it's gone. But even that is not completely sure, because we don't yet know from a theoretical point of view, if you were allowed, for example, to collide two black holes together, nobody knows what the effect of this would be, whether some of the matter that had fallen down would be regurgitated. That's one of the questions theoreticians argue about, but we don't yet understand.
As astronomers search for a huge black hole in space, nuclear physicists search for a tiniest particle, the quark, out of which everything on Earth may be made. It has not been found, but some wonder privately whether the quark might really be a miniature black hole.
The astronomers have now been doing far better than the particle physicists. Whether this will go on, of course, I don't know, but it looks likely it will go on for quite a while. We are just starting to open up a whole lot of new channels, new windows through which we're looking out at the universe with various kinds of infrared, ultraviolet telescopes, X-ray telescopes, neutrino telescopes and all kinds of other things with which one is seeing objects which were not visible in terms of old-fashioned light.
So many mysteries to be explored. The invisible quasars, which create radio energy stronger than any known on Earth. The pulsars, spinning dead stars that send out rhythmic radio pulses. In the center of a cloud of star debris called the Crab Nebula, a pulsar spins so fast that we hear its pulse 30 times a second. And beyond all imagining, regions of matter and antimatter colliding, spreading waves of energy raging through space. The tool for exploring these things and for searching after life in the universe is radio astronomy, a system impossible before the computer. At Stanford University, Dr. A.R. Thompson.
Since we have 5 antennas, there are 10 ways in which we can combine the signals from them in pairs. We take those 10 combinations of signals, and a computer in our laboratory samples the outputs, and we can combine this data in such a way as to make a map of the sky.
What the radio maps have begun to reveal contradicts the widespread belief that the universe always existed. The radio sources give a picture of the universe not as it is now, but as it was billions of years ago. For the sources are very distant, and it takes that long for the radio waves to reach us. What we see and hear is not what is, but what was. These radio signals show a universe that had more energy billions of years ago than it has now, and still farther back in time was quiet. This may mean that the universe had a birth date, a single explosion about 13 billion years ago. Its matter is still flying apart, but appears to be slowing. Its gravity may one day pull it back toward the center, perhaps to disappear finally into the biggest black hole ever, or to explode again. Before that happens, there are about 80 billion good years left, time enough to make contact with life in many other worlds. To determine how, NASA began a study called Project Cyclops. Its director is Dr. Bernard Oliver.
Within 100 light years of the Earth, there are some 10,000 stars, and about 10% of such stars are thought to be likely candidates for planetary systems that could support life. Out to 1,000 light years, there are some 10 million stars, and again, 10% of these could represent possible candidates. We are contemplating a huge antenna array comprising upwards of 10,000 radio astronomy dishes. These would be interconnected so that their signals would all add together to produce the combined effect of one single large aperture that big. So we're talking about a receiving area that maybe covers dozens of square miles.
There are certainly large odds in favor of there being other inhabited planets, or planets that are inhabited. One thing we don't know is, of course, how long a civilization persists when once it's reached the technological stage in which it would be interested in trying to communicate with other worlds.
If civilizations exist for a substantial length of time, and by that I mean maybe hundreds of thousands or millions or even billion years in an advanced state, then we can certainly say that we are going to be among the more naive of them that can communicate, because we've only been able to do so, if indeed we now can, for something in the order of 10 years.
How long mankind will continue to inhabit this planet and be interested in trying to do, in the problem of communicating with other beings, we don't know.
We certainly wouldn't get in touch with anyone that was less advanced.
If civilizations survive their own technology, and if they remain curious, there may indeed be a galactic superculture to search for.
We do have a place ourselves going out into space, and I expect we shall. I expect it will be a major part of the life of the human species, and in the long run, ultimately, small groups of people will be able to roam around the solar system more or less on their own independently. because I believed that, I worked for a year on a nuclear space propulsion system called Orion. And it's a system that uses bombs to propel a ship through space. And it turns out this is much more sensible than it sounds. The bomb explodes outside the ship. The ship has shock absorbers which intercept the debris and convert an explosive impulse into a smooth one.
Men will certainly explore the solar system one way or another. But to meet other intelligent life, we may run against a wall of time. Someday, an astronaut will travel at nearly the speed of light and reach the Andromeda galaxy, having aged only 28 years thanks to relativity. But his first message home will find an Earth 4 million years older than the one he left. His time will have stretched, but ours will not. There are fewer than 10 promising planetary systems in our galaxy that allow a round trip within a lifetime. If we find life in them, is it intelligent? Yet to reach any farther, we will somehow have to assure that our dreams outlive our societies and weather the storms of history. Or at least, so it all seems now.
Back, I think it was in 1935, Lord Rutherford, who was one of the outstanding nuclear physicists of the day and one of the outstanding physicists of all time, was asked what the chances were that man could exploit the energy that physicists, he, outstandingly, had been able to discover locked in the nucleus of an atom. His answer was nonsense. It will never happen. People who say that are talking pure moonshine.
Not 10 years later, Lord Rutherford's impossible actually took place. This was Stonehenge. Here, a society long forgotten tried to make sense of the universe. The questions are lost with the answers. The people left no record. But their questions were probably like ours, 2,500 years later. These are our monuments to the same curiosity. Huge antennae to hear the voices of the universe. Enormous cyclotrons to explore the nature of matter and find what holds things together. Will ours, too, be a quest in vain?
The question is often raised, what is the use of it all? Why should society invest $250 million in the construction of this machine and $50 million a year to run the laboratory and to do experiments?
It's marvelous that Congress votes the money for it, and I hope they go on voting the money for it. But I wouldn't try to bamboozle the public into thinking that this is really going to have any big payoff for them.
Neither Gelman nor I will claim that we shall find quarks at this machine. He's quite doubtful himself nowadays. If it's not quarks, it may be something else.
Feynman remarked once, if you want to find out how a Swiss watch works, one of the worst ways to find it out is to bang two of them together, which is what we do in the scattering experiments.
The theory is a mess in the sense that there isn't any theory. There are little bits and pieces, cookbook recipes for calculating one thing or another. There isn't any coherent body of ideas that pulls the thing together.
But there certainly are groups of people, one of them is Professor Chu's group at Berkeley, who believe that the present particles are made out of each other, so-called bootstrap hypothesis, and that we are at the end. That theory is not in an any more convincing state than the others, I think.
Maybe we were too cautious not building bigger devices. Right now, I think we are sort of wasting our time with this.
Perhaps there is a galactic superculture that we may be eligible to become members of.
Perhaps. But first, there's one basic puzzle to be solved. Long before men dreamed of atoms or discovered the nucleus, they wanted to understand what matter really is, what holds it together, why doesn't it fly apart? 40 years ago, this early cyclotron was built by physicists in Berkeley. It had an acceleration ring 10 feet around, and its purpose was to learn what holds the nucleus of an atom together. The latest cyclotron covers more than a square mile of farmland in northern Illinois. Its ring is 4 miles around, It makes a beam of electrical particles 2,000 times stronger than the biggest lightning bolt. There have been many accelerators between these two, each bigger than the last. Each failed to discover what holds the nucleus of atoms together. What they have revealed is that instead of a few basic particles in the atom, there are hundreds of particles in bewildering variety. But whatever holds the core of an atom together against its own explosive force is still nature's most precious and closely held secret. Physicists call it the strong force, and they can tap a little of it in a bomb or a nuclear power plant, but they don't understand it. And why are there so many particles? They yearn for a simpler picture. They may be getting close. At the controls in Illinois, Dr. Edwin Goldwasser.
We are now in the control room of the latest in the long line of these accelerators, which really you can describe as microscopes. We'll be looking at the smallest structures that have ever yet been attainable to man, because our energy is higher. With these particle accelerators, the energy is analogous to the magnification of a microscope. The higher the energy we have, the smaller the objects we can look at.
The purpose of these huge voltage generators is to subject matter to the kind of energy that created the universe. What happens then is something we have never seen, although Albert Einstein predicted it in 1905. In the accelerators, particles of atoms are pushed to nearly the speed of light, the maximum in nature. Then an astonishing thing happens. As yet more energy is pumped into the particles, they put on weight. Pure energy somehow turns into matter. Stranger yet, at this speed, time slows. In the most literal sense, accelerators are time machines. If a physicist could ride an electron through the 2-mile accelerator at Stanford, we would hear the effects of relativity, the stretching of time, like this.
Energy is transferred from the electromagnetic field inside the guide to the electrons. They accelerate to about the speed of light, and after that, the increases in the energy or the momentum of the particles and not in their speed.
The accelerator is 2 miles long. It has 240 high-powered Klystron tubes. The machine is poised on for a moon position.
The voice would slow, because in the accelerator, time is stretched for a particle speeding toward its target. The pieces flying from its collision with the target are photographed as they streak through a liquid. In thousands of photographs, physicists search for clues. What happens to matter when its tremendous binding force is broken down by collision? And what is that force? Through these photographs, we may finally learn the answers. The machinery is immense and costly. It is a clumsy way, but we have no other. And it is beginning to work. We can break into the atom, even into the nucleus. Now we want to break into the infinitesimal proton itself, 100,000 times smaller than the atom. In the 30s, physicists thought the proton was basic. Now they think it has something else inside. And that tiny something may be our answer.
We may find a new simplicity. We might, for example, find another new particle, which is the last thing we need at this stage of our work. On the other hand, we may find one that has been proposed which would exist in a threesome. These particles have been named quarks by Professor Gell-Mann, who created the idea. In his scheme, from these 3 quarks, it is possible to construct not only neutrons and protons, which we have known for a long time, but also all these other hundreds of particles that we've discovered in the intervening decades.
The experimental physicists place their hope in instruments. Theoretical physicists place their hope in the mind. At the Institute for Advanced Study in Princeton, Professor Dyson.
At the moment, the experiments are beautiful, but the theory is just a mess. And it's questionable whether doing more and more of these beautiful experiments is really going to help matters for us theorists. What has been unusual is that physics did have a very beautiful theory, which worked extremely well and explained almost everything until about the last 20 years. There will certainly be ultimately a new and much more comprehensive theory. What we don't know is how close we are to it. thing that bothers physicists, particularly somebody like me who's just sitting here in Einstein's office, is that in some way we don't feel very adequate. I mean, we are obviously not as deep and as philosophical as he was, and whether that bothers you or not, of course, is a matter of temperament. Einstein had this extraordinary feeling for the deeper meaning of ideas. Somehow he never needed to look at details very much. I mean, his discovery of relativity came from pure thinking, really from nothing more than just a general knowledge of the theory of electromagnetism and a feeling for the basic realities of the universe, which somehow he had. At the present time, physics seems to be in an unphilosophical phase, and this already was true in the last 20 years of Einstein's life. In some way, he was not any longer, at the end of his life, in the mainstream of things. He was out of sympathy with a great deal that the younger people were doing. His own philosophical way of looking at physics just didn't seem to be the way to go to the younger people. One of the characteristic features of the whole of modern physics in the post-Einstein era is that it depends on counting experiments, that everything we do, even in astronomy, is basically a matter of counting particles. We count photons. If your view of the universe is based on this kind of a counting experiment, there's no way in which you can look at things in the way that Einstein did, as entirely a continuous process. In some sense, there is a basic chance involved in whether a photon hits your detector at a particular moment or not. Now, this element of chance in the universe seems to be very basic when we don't understand how one could even think about it in any other terms at the moment. But for Einstein, it was an anathema. He just wouldn't accept it. And he said, God does not play dice, and that was it as far as he was concerned. We just happen to believe that he does.